All right, so we're on to our last example problem of this module. I've set up a circuit right here, and I want to determine, as you can see from the instructions, I want to determine VW, VX, VY, VZ, and VS in the following circuit. This is a problem that's tailor-made for mesh analysis. You can see that it could obviously be solved using superposition as well. There are multiple sources in this circuit, but because I have a current source and because I haven't done a mesh analysis problem yet, I think that mesh is probably going to be the best way to solve this one. So I'm going to go ahead and solve it using mesh. And of course, if you want to use the solution to practice and try to solve this using superposition as well, just to get even better at solving circuits, you're more than welcome to. But the first step of mesh analysis, if you remember from the general process, is to define the loop currents for each loop in the circuit. Okay, so like I said, I like to define, especially when I have two currents coming together that are going to sum and ultimately flow through a resistor like this, I like to define the currents one clockwise and then one counterclockwise. I do that for the purpose that the currents sum when they go through R2, and I just like the way that the math works out better. But of course, you can define your currents any direction you like. And then with any loop that has a current source in it, like this one here, this loop here, it makes sense to define the current in the same direction that the current is flowing, because then I can just straight up say that that loop current is something that I already know. It's equal to the value of the current source, right? Because the current source basically tells me how much current is flowing in that loop. So if I define my current in the same direction, then I already have one of my variables. So if you ever see a problem with one of the loops having a current source, right off the bat, mesh analysis is the answer, because it eliminates one of your variables and the problem becomes very simple. Okay, so I'm going to go ahead and define my third one just like this, and I'll go in there and write all my plus minuses on my resistors just before I start doing this problem. I've got a plus minus, plus minus, plus minus, and then this one here and this one here. All right, and then let's just call this I1, I2, and I3. All right, so those are our three unknowns. Obviously, all the voltages are unknown, but if you remember from the mesh analysis intro or the general process slide, I said that once we find the currents, it's trivial to find the voltages. Hopefully you understand why. It's just because once we get the currents, everything is just Ohm's law from that point forward. So let's go ahead and try and solve for these currents. In this video, I'm just going to set up the equations. I'll do the 3 loop equations, and then I'll end that video, or I'll end this video, and then I'll move forward by doing the algebra in the video to follow. Okay, so let's start with the first loop, and I'll just keep it in terms of variables for now, so that we're not going to start plugging things in yet. There's no need to plug all these values in that I've provided just yet. We'll just do the algebra with all the mathematical symbols or all the variables for now. Okay, so let's start with this loop here, right here, right? And I'm going to start at this point, and I'm going to go around the loop this way. Okay, so starting here, I go across this voltage source. Of course, I'm going to go plus V1, so I'll just write V1. This will be my first equation. V1, then across R2, remember I have two currents, right? I1 and I2 both flow in that resistor. So for the current through that resistor, I need to write I1 plus I2, and then multiply that by R2. And then I keep going around the loop, right? And I get to this resistor, and the voltage drop across that resistor is just going to be I1 times R1, right? So minus I1 times R1 equals 0, okay? So that's my first equation for my first loop. Now let's write the equation for my second loop. Very similar. I'm going to start here and go this way. So going across V2, I go up by value of V2, so I'm going to write V2. Then I drop across R3. Now this is where this problem differs from ones we've seen in the past. I have to keep track of the fact that I have I2, right, and I3 in this circuit, right? So the current flowing through R3 here is I2 in this direction, and it's I3 in that direction, right? You can see this I3 is flowing in the top loop, so I need to make sure I keep track of that. And I'm going to get that the drop across R3 is going to be equal to I2 minus I3 because they flow opposite one another, right? Multiplied by R3. And then the last one is this same resistor here where I have I1 and I2 both flowing, right? So that one's going to be minus I1 plus I2 times R2 equals 0. Okay, so that's my second loop. All right, so my third loop, right? Well, this is the one I was talking about a little bit earlier is, you know, I could start here and start going this way and try to start going around this loop. And I realized that I run into a small issue, but it's not actually an issue. It's actually fantastic. I don't know the voltage across a current source, right? I can't say V over R is the current here because I don't know the resistance of this, right? So I can't use Ohm's law to determine the voltage across this current source, okay? However, what I'm ultimately looking for is a third equation. And my third equation here can simply be that I3 is equal to this current, right? This current source forces a current I1 to flow in this loop. So, you know, maybe, you know, actually, now that I'm looking at it, this would be a terrible thing to call I1 since one of my variables is I1. So let's just call this IS. And I'll come down here and change it too. We'll call it IS. Okay. And so the current IS is the current that's going to flow. That's 50 milliamps. That's the current that's going to flow in this loop. And I3 is the current that flows in that loop. So I can just straight up say that I3 is equal to IS, which is 50 milliamps, right? And so those are my three equations. Now I have an equation for I3. I can plug that value in for I3 here. I can plug it in for, oh, there's no I3 here. But once I plug it in for I3 here, now I have an expression here that's in terms of I1 and I2. And I have an expression here that's in terms of I1 and I2. Now I have two equations, two unknowns, and I can go ahead and solve my, my system of equations. So let me just rewrite equation 1 now. Of course, it's the exact same, so I'm just going to copy and paste it. Nothing changes there. And then for this equation, I guess I could just grab the 2 as well. I have to plug in, instead of I3, I'm going to plug in IS. So let's go ahead and do that. IS. And now I have all of my variables here are known values except for I1 and I2. I have two equations, two unknowns, and I can go ahead and carry out the algebra, solve for my I1 and I2. And once I get those currents, I can very easily find the voltages in my circuit. Okay, so I'm going to go ahead and end this video right here. Now that it's set up, I'm going to do the algebra in the next video, carry out the substitution process, and then we'll go ahead and plug in values and solve for these voltages. All right, so I'm going to end the video here.